The topic of this video is optimum receiver for digitally modulated signals over additive white Gaussian noise channel, or AWGN channel. Previously we had discussed about representing signals as vectors. Okay, so we are going to use those concepts to discuss the concepts of today's lecture. So we are going to consider the transmitted signals in terms of their vector representations. So previously we denoted the time domain waveforms Sm of t, and we had m such waveforms to represent each of the m possible symbols, right? So for example, if you had 2 bits per symbol, then we have 2 power 2, which is 4 possible symbols. So k here denotes the number of bits per symbol, and m denotes all the possible symbols, and each of these m symbols is represented by a waveform which we denote as Sm of t. And because we have m symbols, there are m waveforms denoted as S1 of t, S2 of t, and so on up to S capital M of t. So these denote our transmitted signals. So we are going to transmit these signals over some communication channel, and we had seen the vector representation previously of these time domain signal waveforms as vectors in an n-dimensional signal space. So each waveform S1 of t, S2 of t, and so on can be represented as a vector of length n, and that vector we denote simply as Sm, right? For S1 of t, the corresponding vector is S1. For S2 of t, the corresponding vector is S2, and each of these vectors is of length n. What are the elements of these vectors? What do these represent? These elements represent the projections of the signal onto the n basis functions. So we are using an n-dimensional space to represent these waveforms as vectors, and because it's an n-dimensional space, that means we have n orthonormal basis functions. So each element of this vector is nothing but the projection of the signal onto the corresponding basis function. So S11 is the projection of S1 of t onto the basis function phi1 of t. Similarly, S12 is the projection of S1 of t onto the basis function phi2 of t, and so on. So the projections of the signal S1 of t onto each of the n basis functions become the elements of the vector representation of the signal. Similarly, for S2 of t, it is the projection of S2 of t onto the basis phi1, and so on. So we have the projections of S2 of t onto each of the n basis functions becoming the elements of the vector representation of the signal. Okay, so like that we can represent all our m signals as a vector representation in an n-dimensional space, where the n dimensions or axes are given by the basis functions, and all the basis functions have unit energy and they are orthogonal to each other, so we call them as orthonormal basis functions, and we have n such basis functions. So the signal S1 of t is represented in the n-dimensional space as a linear weighted linear approximation of the basis functions, where the weights associated with each basis function are nothing but the projections of the signal onto the corresponding basis function. So we have a weighted summation of the basis functions to represent the signal Sm of t in general, right? Now when we transmit any one of these signals, S1 of t or S2 of t or S3 of t, in general Sm of t, over an additive white Gaussian noise channel, what does the received signal look like, or what is the effect that is caused by the the additive white Gaussian noise channel. So the effect is that, as the name suggests, it's additive white Gaussian noise channel. That means the channel adds noise, and the noise that gets added to the transmitted signal is white. By white we mean that the power spectral density of this noise is flat. That means it has a uniform power spectral density at all frequencies, and it is a random signal. So the noise is random with the Gaussian distribution, and it also has zero mean value. So the mean of this Gaussian distribution is 0. So with that information, we can now denote the received signal R of t to be the transmitted signal Sm of t plus the noise signal N of t. So that gives us the received signal R of t. Now, when we look at the received signal R of t, we want to analyze this received signal R of t over a duration t, which denotes the symbol duration. So we represent each symbol over a certain duration of time, which we call as capital T, and we are interested in observing the received signal R of t for that duration of time and making some decision about what was transmitted. So all our analysis would be restricted to that particular symbol duration, which goes from 0 to t. So R of t is the received signal waveform, Sm of t is the transmitted signal waveform, and N of t is the noise waveform. And the noise waveform is white. That means it has a power spectral density which is constant over the entire frequency range. So the power spectral density is given by the same value N0 by 2 for all frequencies. Okay, and it has a Gaussian distribution with a mean value that is equal to 0 and some standard deviation and hence some variance. Okay, now from the definition of white, that means when the power spectral density is flat, we can determine the autocorrelation function, which is the Fourier transform of the power spectral density, or the inverse Fourier transform of the power spectral density. So the autocorrelation function is given as N0 by 2 delta of tau. That means that the noise that we are seeing here, that we are considering to be added on the channel, is uncorrelated. That means this autocorrelation is 0 for all values of tau which is not equal to 0. So when tau is equal to 0, delta of 0, the impulse function is 1 when tau is equal to 0. So 1 into N0 by 2 will become N0 by 2, and that is when tau equal to 0. And for all other values, delta of tau becomes, for all other values of tau, delta of tau becomes 0, and therefore the autocorrelation becomes 0. That means the noise process that we are seeing here is uncorrelated. And as we have seen in our earlier chapter of random processes, the power of a random signal is can be obtained by evaluating the autocorrelation function at tau equal to 0. So when you put tau equal to 0, the answer that you get in the autocorrelation, that represents the noise power. And for a random process like the Gaussian process, which is also ergodic, the power is represented by its variance when the mean value is 0. So since we are talking about zero mean Gaussian noise, the power that we have here also represents the variance of the signal, or vice versa. The variance represents the average power when the mean value is 0. Okay, so now we have all the information about the received signal, the transmitted signal, and the noise signal. Now we see what happens when we combine this signal, the transmitted signal, with the noise, and what is the objective at the receiver side, and what do we want to do with this received signal. So what is the purpose of the receiver, and what is the functionality that we need to perform at the receiver side. The objective of the receiver is to observe this received signal R of t and then determine by observing R of t as to which of the m possible signals have been transmitted, and it has to do so in such a way that the probability of making an error should be minimized. So the job of the receiver, or the objective of the receiver, is to make a decision as to which of the m possible signals was transmitted by observing the received signal R of t with a minimum probability of error. It has to minimize the probability of error. So that we call as an optimum receiver, which minimizes the probability of error. Now the function of the receiver can be divided into two parts. So the first part we call as the demodulation step, or the demodulation part, and the second step is called the detection part. So the demodulation is done or performed by the demodulator, and the detection is performed by the detector. Okay, now we are going to look at the functions of each of these, what exactly they do, but for the rest of today's lecture we will restrict our discussion onto just the demodulator part, and even within the demodulator we will look at only a specific type of demodulator in this particular video, which is called as the correlation type demodulator. Okay, so that would be the focus of our discussion for today. So let us first see what is the function of the demodulator. The function of the demodulator is to convert the signal waveform R of t into its vector representation, which is a vector of length n. So from the waveform it has to transform it into a vector representation in the n-dimensional signal space. So the job of the demodulator is to convert from the waveform to its vector representation, and the vector R corresponding to the received signal waveform R of t has elements R1, R2, R3 up to Rn. So it is of length n because it's going to be in an n-dimensional space, and each of these elements R1, R2, R3 and so on represents the projection of the received signal R onto the basis function phi1. So R1 is the projection of R of t onto the basis phi1. R2 is the projection of R of t onto the basis phi2. R3 is the projection of R of t onto the basis phi3, and Rn is the projection of R of t onto the basis function phi n of t, right? So these denote the projections of the received signal onto each of the n basis functions, and that way, by putting these projections as elements of a vector, we get the vector representation of the signal waveform R of t. Then the job of the detector is to observe the vector R and decide which of the m possible transmitted signals has been transmitted. So that is the job of the detector, and again it has to do so such that it minimizes the probability of error in this decision making. So when the error probability is minimized, if we design the detector in such a way that the error probability is minimized, we call it as an optimum detector. Okay, again the discussion on the detector would be a subject of a separate lecture or a separate lesson, and we will do that maybe in a couple of weeks, but for now we are going to focus on the demodulator part. Okay, right. If you look at the demodulator implementation, we can do the demodulator implementation into two types, in two ways. The first type of demodulator is called as the correlation type demodulator, and the second type is called as the matched filter type demodulator. And the focus of our discussion for today is going to be on the correlation type of demodulator. So we will discuss today how the correlation type of demodulator works, and then once we convert the signal, which is the general functionality of the demodulator, is to convert the waveform into its vector representation. We will also analyze what is the probability density function of that received signal, vector elements, and so on. So we can decide how to apply this to the detector so that the detector can be designed in an optimum way. Okay, so we'll talk about that as well towards the end of the lecture. Now, the principle of the correlation type demodulator is similar to a topic which we have discussed a few lectures back when we discussed about the signal space representation of signals using basis functions. And if you recall, we looked at it from two perspectives. The first perspective was to synthesize the signal in terms of the basis functions by using the projections and the basis functions, and the second aspect was to analyze a given signal by using the basis functions. That means we analyzed and found out what is the projection of the signal onto each of the basis functions, and those projections became our vector representation. So that is exactly the same principle or perspective that we are going to use today in the correlation type demodulator, where we are going to analyze the received signal R of t using a set of n orthonormal basis functions. So we have n basis functions to analyze the received signal R of t. That means we are going to find the projection of the received signal R of t onto the basis function phi 1 of t, phi 2 of t, phi 3 of t, and so on up to phi n of t. So we will find the projection of the received signal onto each of the basis functions. Now, we assume that these n basis functions are sufficient to represent all the m possible transmitted signals. So that means we assume that the basis functions span the signal space. That means they can represent all the possible signals of interest, which are the signals that are going to be transmitted. So the n basis functions are sufficient to represent all these m possible transmitted signals. Okay, so that means the terminology is that these basis functions span the signal space. Now, if it doesn't span the signal space, it means that there might be some or any of the m possible transmitted signals which cannot be represented in terms of these basis functions. So if it cannot be represented, then we won't be able to detect, demodulate, and detect it, right? So therefore, we want to ensure that these basis functions span the signal space. And for our analysis, for our discussion for today, we will assume that these are sufficient. That means we will assume that these basis functions span the signal space. However, these n basis functions do not necessarily span the noise space. Okay, while they do span the signal space, the n basis functions are not sufficient to represent the entire noise signals. Okay, because the noise signals are random and each waveform is going to be different from the other noise waveforms. So therefore, the n basis functions do not span the noise space. So that has a consequence in terms of the noise that is captured by the basis functions in our representation, but we will eventually show that the noise which is missed out in the correlator it does not affect our analysis, and it becomes irrelevant to the decision making process. So therefore, we can safely ignore it. Okay, the functionality of the correlation receiver, where we compute the projections of the received signal onto the n basis functions, can be seen as an implementation by this diagram, where we have n parallel cross correlators which compute the projections R1, R2, R3 and so on up to Rn. So since we have n projections, we have n parallel cross correlators, we call them, right? So which compute the correlation between the received signal and the basis function, which is nothing but the projection of the received signal onto that particular basis function. So R1 is the projection of the received signal onto the basis phi 1, which is given by this equation. The projection is given as the integral of r of t into phi of t. So integral r of t into phi j of t is rj in general, right? But we know that the received signal r of t is the sum of the transmitted signal Sm of t and the noise signal n of t. So we put that into our in place of the received signal r of t, and then we can divide this integral into two components, where we have the first component which denotes the projection of the transmitted signal onto the basis function phi j of t, and the projection of the noise signal onto the basis function phi j of t. So each of these projections R1, R2 up to Rn, which denote the projections of the received signal onto the basis functions, onto each of the basis functions, is nothing but the sum of the projection of the transmitted signal on the corresponding basis function and the projection of the noise signal onto the corresponding basis function. So that means R1 is equal to Sm1 plus N1, R2 will be Sm2 plus N2, and so on and so forth. So that way we can find the projections of all the on all the n basis functions, and we see that the projection of the received signal is the sum of the projection of the corresponding transmitted signal and the noise signal onto a particular basis function. Okay, and that is what we are trying to highlight here in more detail. So the projection Rj of the received signal is the sum of the projection of the transmitted signal onto that same basis function and the projection of the noise signal onto that same basis function. So we see that the basically what we're trying to show here is that the even in terms of the vector representation, the received signal is simply the sum of the transmitted signal plus the noise signal. Okay, so we have the vector representation of the received signal, which is R1, R2 up to Rn. These are the elements of the vector, and each of these elements is the sum of Sm1 plus N1. Sm1 is the element of the vector representation of the signal Sm. N1 is the element of the vector representation of the noise component, right? So basically each element is the sum of the signal component plus the noise component, as we see more clearly in these equations here. So the vector R, which denotes the vector representation of the received signal R of t, is a vector of length n, which is nothing but the sum of the vector representation of the transmitted signal, which is of length n, and the noise and the vector representation of the noise signal n of t. Okay, but what we need to bear in mind here is that the noise signal that we take into consideration here represents only that noise which lies within the signal space, and that can be represented using the n basis functions. All the noise which cannot be represented using these basis functions, or which lies outside the signal space, is not included in this received signal in these elements R1, R2 and so on. That means the noise component which is included in these components R1, R2, Rn and so on is only that noise which lies within this signal space represented by this n-dimensional or the n orthonormal basis functions, okay, which lies within the n-dimensional signal space. The noise which lies outside this is not reflected in these projections, okay, in these components R1, R2, and so on. So the noise vector here does not include the noise which is outside the signal space, but the actual received signal is the transmitted signal plus the noise which has been captured by the correlator and the noise which has not been captured, which we denote as n dash of t. So n dash of t here denotes the noise which lies outside the signal space of this n-dimensional space that we are interested in, okay, and that is not included in this vector representation. So this has been excluded here, but our R of t is actually the noise that has been included and the noise that this our correlator did not take into account, did not take factor of, right? So that is missed out, but for completeness we represent the entire signal plus noise. So that's the total noise. That's the noise which lies within the signal space, and that's the noise n dash of t which lies outside the signal space. So the noise which lies outside the signal space is nothing but the total noise minus the noise that has been factored into the signal space, right? So that difference gives us the noise which is outside the signal space of interest for us. However, we will show later, and we will discuss towards the end of the lecture that not including this n dash of t in our analysis. So if you look at the vector representation R, we don't have this n dash of t over here, okay. So not having that does not affect our analysis and our results, and therefore this n dash of t is not relevant for our detection process, and therefore we can safely ignore this n dash of t. So the decision that the detector makes as to which of the m symbols or signals was transmitted is based completely on the correlator outputs R1, R2, R3, and so on. So it is based completely on these elements, which does not include any information about n dash of t. So just by observing these elements, the detector is able to detect, and because this n dash of t does not affect our results, we will simply ignore it. Okay. Next, what we are interested in is to identify or to determine what is the probability distribution of the vector elements of the received signal vector R. And to do that, we need to first look into what is the probability distribution of the transmitted signal and the noise signal vector, right? So because the received signal vector elements are the sums of the transmitted signals vector elements and the noise signals vector elements. So R1 is SM1 plus N1, R2 is SM2 plus N2, and so on. So these depend on the transmitted vector and the noise vector. So the received vector depends on the transmitted vector and the noise vector. So in order to determine and understand the probability distribution of the received signal vector, we need to understand what is the probability distribution of both of these. And for a start, we will see that, or we know that, the transmitted signals are deterministic. We have chosen what we are transmitting, so the transmitted signals Sm of t are deterministic. They are not random, so they are deterministic. So because the transmitted signals are deterministic, their vector representation, and therefore the elements of its vector representation, are also going to be deterministic. So the transmitted signal part is deterministic. So this part here, all the elements in the transmitted signal vector are deterministic. So we know exactly what they are, and there is nothing random about them. The randomness comes from the noise part, because the noise that got added to the transmitted signal on the channel is a random signal which has a mean value of 0, and it has a Gaussian distribution and a variance given by n0 by 2, as we have seen earlier. So therefore, the elements of the noise vector will also be random with the same distribution, which is the Gaussian distribution. They'll have the same mean value, which is 0 mean, and the variance of these elements will also be the same as the variance of the noise that got added. So therefore, the noise vector here, these elements of the noise vector are 0 mean Gaussian random variables with the mean with the variance equal to n0 by 2, which is the same as the variance of the noise process that got added. So we want to represent the PDF of each element of the noise vector. So since it is a Gaussian distribution with 0 mean and variance sigma square, so let us first write the general equation for the Gaussian PDF, which is given by this equation, where in this equation this mu denotes the mean value, and the sigma over here and here denotes the standard deviation, which is the square root of the variance. So that means the sigma here is here and here is square root of n0 by 2. So we are just going to substitute mean equal to 0 and sigma equal to square root of n0 by 2 in this equation, and that would give us the probability density function of each of these elements of the noise vector, the probability density function of n1, of n2, of n3, and so on. So in general, for any ni, so we can write the PDF of any of the elements by substituting mean 0 and standard deviation square root of n0 by 2. And when we substitute it and simplify it, we get the PDF to be given of each of the elements of the noise vector to be represented by this equation, by this particular equation, right? So just to, in place of sigma, we had put square root of n0 by 2, and here also in place of sigma it's square root of n0 by 2. Ni minus mean is 0, so that disappears, and when you square the square root disappears. So n0 by 2, you can write it as 2 by n0, so the 2 and 2 cancel out, and here also the root 2 and root 2 cancel out, so you have 1 by pi n0 under the root, which we have put as power half e power minus ni square by n0. The 2 and 2 is cancelled, right? So this is what we have as the PDF of each of the elements of the noise vector. Now what we are interested in is to find the PDF of the entire noise vector, which is of length n. So we know that the PDF of each element is given by this equation, which we have seen here, and that is the same for each of the n's, right? So n1, n2, n3, all of them have the same PDF, and we want to find the PDF for the entire noise vector. And to find the PDF for the entire noise vector, we make use of the fact that the elements ni of the noise vector are all independent of each other. How do we know that? We know from the fact that when we talked about the autocorrelation, we saw that the autocorrelation of white Gaussian noise is a delta function. That means one sample and another sample of noise is going to be uncorrelated or independent of each other. So therefore, each of the elements of the noise vector, n1, n2, n3, and so on, they are all independent of each other. And since they are independent of each other, their combined PDF is simply the product of their individual PDFs. So we will take the PDF of n1 into the PDF of n2 into the PDF of n3, and since they are all having the same PDFs with the same mean and the same standard deviation, it is just simply P of ni power n, right? So we can write that as the product of the individual PDFs, and because they are all the same PDF, we can simply write it as power n. So when we take it to the power n, so this power half to the power n becomes power n by 2, and the powers, when you multiply the powers, the exponents get added, right? E power ni squared by n1 squared by n naught into e power n2 squared by n naught, and so on, is e power n1 squared plus n2 squared by n naught, and so on, right? So we get this summation term here. So we get the PDF of the noise vector to be given by this expression. Okay, so now we have the PDF of the noise vector. Now our bigger objective is to find the PDF of the received signal vector on the condition that any particular of the m signals has been transmitted. So we want to find the conditional PDF of the received signal vector r on the condition that a particular Sm of t has been transmitted. And again, for that we use the fact that the transmitted signal is deterministic, the noise signal is zero mean Gaussian noise, and the received signal is the sum of the transmitted signal vector plus the noise signal vector, right? So this is zero mean and variance n naught by 2. This is a deterministic signal, so therefore the mean of each element is itself. The mean of each element here is 0. So therefore the mean of R1, R2, R3 would be the mean of this plus the mean of this. So the mean of R1 is the mean of this plus the mean of this. The mean of SM1 is SM1, and the mean of N1 is 0. So therefore the mean of R1 is simply SM1. Similarly, the mean of R2 will be the mean of SM2, which is SM2, plus the mean of N2, which is 0. So the mean of R2 in effect will become SM2. Or in general, the mean value of each of the elements of the received signal vector are simply the corresponding projections of the transmitted signal onto the basis function phi 1, phi 2, and so on, right? So we now know that the mean of each of this would be the same as the means of the transmitted signals, number one. Number two, because the transmitted signals are deterministic, and to that deterministic we are adding a Gaussian random process. That means the sum of the deterministic plus the Gaussian will result in a Gaussian process. So the received signal is the elements of the received signal vector are going to have a distribution which is the Gaussian distribution, with the mean value equal to these element values. The variance of these will not be affected because there is no multiplying effect here. So therefore the variance of the received signal vector would be the same as the variance of the noise vector, which is n naught by 2. So we'll elaborate that a bit more here. So we have the mean of each element of the received vector r, which is mean of r1, r2, and so on, is simply sm1, sm2, and so on. Okay, as I illustrated here, the mean of r1 is the mean of this plus the mean of this, which is sm1 plus 0, which is sm1, and so on. Okay, so we have the mean of each of the elements of r to be nothing but the projections of the signal Sm onto the basis phi j. Okay, so with that information we can now write the conditional PDF of the received signal vector r on the condition that a particular transmitted signal Sm has been transmitted. And we start off by writing the PDF for each element of the received vector r. So what is the PDF of r1, the PDF of r2, and so on up to the PDF of rn. And we are talking about the conditional PDFs on the condition that a particular signal is transmitted, which is Sm, right? So the PDF, the probability of Rj on the condition that some Sm has been transmitted Again, we use the general equation of the Gaussian PDF, which is 1 by sigma root 2 pi e power minus half x minus mu by sigma the whole square, right? So the mean here is SM1, SM2. In general, it is SMJ, depending on which of the correlator outputs we are interested in. The variance is the same as the noise, which is n naught by 2. Therefore, the standard deviation is square root of n naught by 2. So, and we just substitute these values, and when we simplify this, we get this equation here, which is the PDF of each element of the received signal vector R. Okay, and it is going to have a mean value which is SMJ. It's no longer mean 0, because to the 0 mean Gaussian noise some signal component was added, so the mean gets shifted by the same amount. Okay, so we have the PDF of each element of the received signal vector, or the conditional PDF, on the condition that a particular signal SM is transmitted, to be given by this equation. So we can find the PDF of R1, R2, R3 up to Rn. So this J index goes from 1 to n. So to find the probability of R1 on the condition SM, it will be R1 minus SM1 the whole square, right? For R2, it is R2 minus SM2 the whole square, and so on. Okay, so that way we can find the conditional PDFs for each of the elements of the received signal vector. The next thing we want to do is to find the conditional PDF of the entire received signal vector R. We know the conditional PDF of each element now. We now want to find the conditional PDF of the entire received signal vector R, and to do that we invoke the fact that each element of R is independent of each other. And why are they independent of each other? Because R is nothing but the summation of the transmitted signal and the noise signal. So basically, because the transmitted signals are deterministic and the noise signals are random, but they are independent of each other, so therefore these elements are also going to be independent of each other. So when they are independent of each other, the combined PDF or the probability distribution would be the product of the individual distributions. So with that in mind, we can now say that the conditional PDF of the received signal vector R, now this is not the single element of R, this is the entire vector R, on the condition that a particular signal SM is transmitted, is the product of the PDFs of each element of R, which is given by RJ. So we take the PDF of R1, condition that SM is transmitted, into the PDF of R2 on the condition that SM is transmitted, and so on, and we multiply it for all the n elements of the vector R. So that gives us the conditional PDF of the received signal vector R. So we are just going to take this single PDF and multiply it n times, or to the power n. So when we multiply it to the power n, so this term becomes power n by 2, and here it's these terms multiplied n times, so we'll have the summation of these terms for j equal to 1 to n. So, and that is exactly what we have here. So when you multiply the PDF of each of these n times, because we have n elements and each element has the same PDF, so we get the PDF of the received vector to be given by 1 by pi n naught power n by 2 e power minus summation of rj minus smj the whole square by n naught, right? Now what we want to notice here is that this summation term, the summation rj minus smj the whole square, is nothing but the distance squared between the received signal vector and the transmitted signal vector, rj minus smj the whole square. So if we go back to our vector representation, r1 minus sm1 the whole square plus r2 minus sm2 the whole square plus r3 minus sm3 the whole square plus, and we keep doing that for all the n terms. So r1 minus sm1 the whole square plus r2 minus sm2 the whole square. So basically what it means is this summation term here is nothing but the square of the distance between the received vector r and the transmitted signal vector sm. So that can be simply represented as the square of the distance is nothing but the norm squared, right? So r is the received signal vector, sm is the transmitted signal vector. So the elements of r is r1, r2, r3 up to rn. The elements of sm are sm1, sm2, sm3 up to smn. So this summation here is basically the distance squared, which is nothing but the norm squared, right? So we get the conditional PDF in terms of the distance squared, which, and by the way, when I say distance, I mean the Euclidean distance between the vector r and the vector sm, right, which is the Euclidean distance between the point in the n-dimensional signal space that denotes the received signal and the point in the n-dimensional signal space that denotes the transmitted signal sm, right? So we see clearly that the conditional PDF has a factor here which represents the Euclidean distance between the transmitted signal and the received signal. So this is what we will exploit in the next step of our decision making, which is the detector's functionality, where we will see that in order to minimize the probability of error, we need to choose the transmitted signal which is nearest to the received signal. So we have m possible transmitted signals. So we need to choose the detector must decide in favor of that transmitted signal which is nearest to the received signal vector, or in other words, the one which has a minimum Euclidean distance with the received signal vector. Okay, that would minimize the error probability of the detector. So that is going to be our topic of discussion in a subsequent lecture, where we will see that indeed minimizing or choosing the or deciding in favor of the transmitted signal which is nearest to the received signal, or the transmitted signal which has the minimum Euclidean distance with the received signal vector, indeed minimizes the error probability of the decision making or the error probability of detection. Okay, so that will be our topic of discussion in our subsequent lecture. And the other topic that we are going to discuss is the second type of demodulator, which is called as the matched filter demodulator. We will also discuss about that and analyze that and look at what is the principle behind the matched filter demodulator. And then we will for both the matched filter demodulator as well as this correlation type of demodulator, we will see what is the optimum detector which minimizes the error probability. And intuitively you can see that the optimum detector would be one which would minimize the Euclidean distance between the received vector and the transmitted vector, right? So if the detector decides in favor of a signal which is nearest to the received vector, that would minimize the error probability. Okay, we will continue with the next topic in our next lecture, which would which would be a discussion on matched filter as well as the optimum detector to minimize the error probability. All right, thank you.